Well, microphone? Sorry? Microphone.
Well, today I was supposed to give my third lecture, and I'm finishing my first lecture. So I will try to mainly finish the content of the first lecture. That means that I will address how to use the NCR. I think so. Yeah? Now it works? Now? Now?
Yeah.
Now? Okay. So I will finish what concerns the application of the hierarchy at equilibrium. And as I explained in my first lecture, this is very similar to the out of equilibrium case once you have used the Nonequilibrium formalism or the Martin-Cijarot formalism. So in principle, if you are able to follow what I will explain today, you could, after that, do for yourself the out of equilibrium case in the case where the system can be expressed via the Nonequilibrium. If you want more details, because always going from in principle stuff to concrete stuff is not always so easy, I will give this extra lecture this afternoon, where some, I think, interesting results will be presented. So, non-perturbative RG. Non-perturbative RG, in fact, I think my point of view is that it should be called in another way. It should be called.
Can you get the board light on, please? Turn the light on the top board.
Right.
It should be called neo-Wilsonian RG. Okay, in the 70s, Wilson developed the Wilson renormalization group. After that, it was quickly replaced by the perturbative renormalization group, which is based on mainly two kinds of renormalization group: the Kalan-Zimanski renormalization group and the Gelman-Lowe renormalization group. And Wilson renormalization group becomes quickly as a old-fashioned stuff. And during the 80s, almost nobody worked on that. And in the beginning of the 90s, mainly because of some works of Vetterich and Morris, people found one way to be able to do concrete calculation within the reformulation of the Wilson renormalization group, which is now called Nonperturbative renormalization group. And the main point is that this reformulation allows you for the formulation of approximation schemes that are not based on perturbation theory. That's the main point. Is as perturbative RG, but the structures of the equation are able to allow you to formulate other kinds of approximation that need not be based on perturbation theory. But I want to recall two equations I wrote last time. The first one is the one-loop correction to the effective action to the Gibbs free energy. It takes this form. Okay? And a particular case of this equation is for the, I wrote a consequence of this equation for the susceptibility. Okay? So in the inverse susceptibility that I call R, can be wrote as R0 plus Q0 over 2 dq for 2pd. Okay? So this is a particular case of this when you calculate for a constant vacuum field and you take two derivatives of the potential. Okay, so this equation shows you the problem. What is the problem we are trying to solve? The reason why we are not able to use perturbation theory, strict perturbation theory, in order to address critical phenomena is that when you perform the perturbative analysis, you see that there are some integrals that appear that go from zero momenta to infinite momenta. Well, I explained last time that you must have the integrals in the ultraviolet, in the microscopic regime given by the inverse of the lattice spacing size in a magnetic problem or the size of molecules in a liquid-gas transition. So there is an ultraviolet scale that cuts you the drive from above. But when you are approaching criticality R, which is nothing but the inverse of the susceptibility, goes to zero, and the integrals then can arrive up to very small momenta, and you have a problem in the infrared. So you are integrating from one step in a whole bunch of scales, and this is a very difficult task. Of course, if you are in a simple mode that can be solved analytically, this is not a problem. But if you are in a situation where you need to do approximation, it is very difficult to perform approximations that are valid in all scales at the same time. I give you a concrete example that shows that this is not a reasonable strategy. If you want, for example, to analyze the structure of molecules, okay? You want to see how quantum mechanics predicts how are the structure of, I don't know, the hydrogen molecule, H. Nobody will do particle physics to do that. Nobody will begin with the structure of quarks, deduce, I would say, see all the quarks running around the nucleus that interact moreover with the electrons. No, nobody do that. People first do an effective theory for the nucleus, replace all the stuff in the nucleus. First, the quarks are replaced by protons and neutrons. After that, protons and neutrons constitute the nucleus, and after that, the nucleus interacts with electrons, and so on. That's how people work. Okay? Even the intermediate states that are atoms. They consider atoms as more or less independent objects, and they make them interact with them. So the strategy that everybody follows in physics is to construct effective theories that allow you step by step to cover intermediate state scales without having to take into account what happens in all microscopic scales below. Okay? That's the normal stuff. But in critical phenomena, we don't know how to do that, mainly because the system becomes what is called self-similar. That is, there is no clear separation of scales as we could have in the structure of the atom or the nucleus. You have a characteristic scale, and you can separate what happens below and above the scale. Here we don't have that. So that's why we have these nasty integrals, because you have many scales that are not clearly separated. Okay? So what is the RGA strategy? Is to say, well, nature do not give us a separation of scales, so let's invent one. Okay? Let's say, okay, there is no clear separation of scale, so let's put it by hand. Okay? That's the first step in the RG. The second step of the RG is to say, well, let's take serious the effective theory strategy. So in order to calculate what happened in a given scale, do not try to deduce it from the microscopic behavior, but from the just previous scale. Okay? And after that, work step by step. Okay? That would be a step. That's the conceptual idea. I will show you how does it work. Okay? So in order to separate scale, the best thing, the simplest thing you can use if you want to separate it by hand, if you have your Hamiltonian H, and you will replace it by a modified Hamiltonian lowercase I with a delta H k, where k is a scale that tells you where the separation of mode is made. So, in practice, the most simple separation of scale that can be done is to use a quadratic extra term. This term is called the regulator term. Okay? That will filter you from the theory all the modes that are below the scale k. So you write it as a quadratic term. R Q squared C Q. So this term it has the Euclidean.
Can you put your microphone a little bit lower?
No, battery.
Okay, thank you. Does it work now? Yeah. So this term has the Euclidean symmetry of the problem. It is invariant by translation and rotation. And moreover, you see, if you take this function, which is called the threshold function, or the regulating function, conveniently, it gives you a separation of modes. So how is the best thing to do? Let's put modes here, Q, and let's put the function here. So what we take is a characteristic scale here, Q, K, sorry, and for momenta lower than K, this will behave as a contribution in the Hamiltonian that gives you a correction to the correlation length. Okay? I recall you that the Hamiltonian takes this form. Hamiltonian takes this form, and R0 can be interpreted both as the inverse susceptibility, and it can also be interpreted in mean field as the R0 is in mean field is the correlation length at the power -2. So you see, at small q, this behaves as a correction to this term. Okay? When q is 0, this will give you a contribution here. So let's call this contribution zk k squared. So forget about the zk for the moment. Let's put k squared. So it makes you R0 modified by R0 plus k. In low momentum modes. So even if your correlation length is divergent, even if it is 0, you still will have, for low momentum modes, a correlation length, non-zero correlation length. And because of the Ginzburg criterion we saw last time, if you have a big correlation length, you are able to control approximation, in particular perturbation theory. So if you have a big correlation length, there is no problem. The problem is that, of course, we will need to move this parameter, because the physical theory is when you remove that. So we will need to move progressively k, and the point is to formulate approximation in order to control this moving. Okay? So once you have added this correction to the Hamiltonian, you have a new Gibbs free energy that I call gamma k, whose precise definition I will give in a moment. And this Gibbs free energy goes when k goes to 0, goes to the full Gibbs free energy. In this case, you remove that, and if you remove that, you will go to the mean free energy. Okay, you will. Without that, you have the mean free energy, the full Gibbs free energy. Okay, but moreover, if you take k very big, let's say approaching the microscopic scale lambda, so there will be no fluctuation at all, because then k is very big, you have a very short correlation length, and so the Gilbert criterion says that in that modifier theory, you are able to apply mean field approximation, because the Gilbert correction is very small. Okay, so in that limit, gamma will become simply the Hamiltonian. The mean field will apply. And of course, you need to move from that point, which is well controlled, to this point, which is difficult, probably smooth. Okay? So how to define this? Well, first of all, we can define the gamma tilde k of phi, which is the usual Legendre transform of the Helmholtz free energy. Okay, this is just the Helmholtz free energy defined not for this Hamiltonian, but for the modified Hamiltonian. Okay, so the exponential of Wj will be the integral of phi of RH minus delta Sk plus dx g. It's just the same definition as before, but now it depends on k because you added this term. You see? This is clear? Well, after that you can perform this Legendre transform in order to go to the Gibbs free energy. But you see, when chi is very big, this functional will not approach the Hamiltonian, but will approach the full Hamiltonian, h plus delta s, because you are able at very big high k to apply mean field. Mean field is well controlled in very high k, but then you will not arrive to h. So the usual stuff is to define gamma k not as the Gibbs free energy, but as the Gibbs free energy minus delta hk. In this way, this functional at big k goes to the Hamiltonian. Okay? So this is the functional we will look at. Okay? So I repeat, you have this scales. K begin here. Here you have the Hamiltonian. At the end you will have gamma, and in the middle you have gamma k that interpolates between them. Okay?
The function R k like general, or is that just like over lambda?
Sorry?
The function RK.
Well, the function RK, you must take it as you want, as long as it has these main properties for any model, let's say. You need to behave as an inverse correlation length at mole Q and go rapidly to 0 at dark Q. Why I ask it to go rapidly to 0? Because I want to interpret this as an effective action where the modes with Q larger than K are included in the path integral. And you see here the modes that have momenta larger than K has not been touched. This is negligible for large Q. So with respect to modes that are much larger than k, I have the same function as that before. I only modified low momentum modes. So I would say this is modes included. And these are the modes to be included. Yeah?
What would you do with an antiferromagnet with three dynamics? Because they have modes at zero momentum and some at non-momentum.
That's a good question. There is a paper that will be published and sent to the archive in the next few weeks by Nicholas Wschebor, where they analyze precisely that sort of stuff. Okay, that's the point. Is when, if I understand correctly, your question is what happens when the single site dynamic is non-trivial. Okay, well, that's. That can be done. It requires a bit to be careful. Okay. So, okay. Well, now I will deduce an exact equation for this function. Okay. But I will not show that the equation is exact. I will try to introduce this equation in a heuristic way to see what is conceptually the origin of this equation. And in the appendix of the notes, the exactness of the equation is shown. Okay? So, how to proceed? Well, take the doesn't erase quite well. Well, take the Gisburg-Landau, the Gisburg correction to the Landau approximation, and let's suppose it is valid. Okay? Let's suppose we are in a perturbative domain, where this is a good approximation. Okay? For the same reasoning, I can deduce that gamma k of phi is equal to h phi plus 1/2 of trace log of the second derivative of h plus arc. You see? Because I introduced a quadratic term, I recall you, delta is like phi r phi. So if I take two derivatives here, I obtain arc. Okay. Do you see that? So this at one loop level, this is the expression for gamma k. Okay? But as I explained to you, I don't want to give an expression that gives you the solution of gamma k in a single step. You see, in this expression, I deduce the expression of gamma k at one loop level from written in terms of h. Okay, but this is the bad idea I stressed before. You don't want to express what happened at this scale k in terms of what happened at the scale lambda. You want to move k slowly and write gamma k in terms of what happened just before. So in order to do that, we'll take the derivative with respect to k. Okay, this term does not depend on k, and the other term becomes trace of dk r times gamma 2, well, h2 is an abbreviation for this second derivative matrix, minus 1. I think here I simply said that the derivative of the logarithm is the inverse, and after that I must use the chain rule and derivate also the r function. Okay?
It says gamma 2, not h2.
No, here it's h. Wait a minute, I'm coming. Okay? Take the derivative, you see? I'm at one loop level. Okay. So you see, the good news
is that this is an integral, but it's dominated by the region of momenta of order k. You don't have anymore an integral over all scales, but for a very short scale. Why? Because I erased the function, but it takes this form, r. So the derivative of r with respect to k goes to 0 very fast when q is much larger than k. So momenta much larger than k do not contribute to this integral. Moreover, the momenta which are more smaller do not contribute neither, because now we added an extra contribution to the correlation length. So the correlation length, to the inverse correlation length, the correlation length is reduced. So in this regime, you will not have nothing. Okay? So this integral is peaked around k. So instead of summing over all momenta, you are summing in a small window. Okay? Do you see that? Okay, that's the good news. The bad news is that we didn't manage still to have an equation for gamma k that do not depend on the microscopic scale, because you still have h here. And I recall you that h comes from the beginning, and we want this step gamma k at k minus delta k to be deduced from gamma k, not from h. Okay? We don't want this function to be deduced from this one function, but for this one. Okay? To be in order, in the spirit of effective theory, you don't want to see what happened to the molecules in terms of quarks. You want to see what happened to molecules in terms of atoms, not quarks. So you want to deduce this theory in terms of that theory and not this one. But at one loop order we are happy, because at one loop order, you see, this is already a one loop expression. So here you can safely replace h by gamma, because the difference is a one loop contribution. So if you replace h by gamma here, the difference will be two loop order. Okay, so at one loop order I can write this equation. And this is exactly what has all the good properties we wanted to. It is dominated by a small amount of momenta, okay, a small shell. It is regular in the ultraviolet and in the infrared. There are no ultraviolet, no infrared divergences. And moreover, in order to know what happened at a scale, we only need to know what happened on a very similar scale. Okay? And now, the good news, the incredible good news, and this is mainly the contribution of Polchinski, is Polchinski, not for this equation, for a related equation, the first one who realized that, is that this equation is exact. Okay? I didn't prove it, because my reasoning was all at one loop order. Okay? I make a lot of one loop order arguments. But in the appendix you can read the proof. It is not a very interesting proof. Okay? The important is the result. Okay? And this equation is exact. Okay? Yeah, second derivative, as before. And this is sometimes called the Wetterich equation. So it depends on which paper you want to quote. It is from 91 or 93. Okay? And that's the NPRG equation. That's what we are going to use now. From now on out, my second lecture begins.
this is a momentum scale you're introducing to infrared light.
Yeah.
Does it have a natural interpretation like the lambda? For example, this looks a lot like, at least the distribution.
Yeah.
It looks like a Fermi function for electrons. So is it, so for example, for electrons or fermions, we use it as the Fermi momentum as the scale? Or what?
No. In fact, this function is quite arbitrary. You should, the form of this function should be think as the order in which you integrate modes. You see, if you take, for example, a very sharp function that way, okay, you are saying I'm integrating very fast these modes and this almost nothing. If you take something here, you say, well, these modes are integrated the same way, but these are a bit more integrated. Or if you take a longer queue, they almost are taken into account more or less at the same time. So, if you take a too sharp function, this is not too good because this becomes non-analytical, near non-analytical. That's not good. Okay. If you take a too flat function, this is not good neither because in that case the idea of separation of scale doesn't work anymore. Okay. So you need something in between. Okay, but if you have anything more or less in between, that works.
So K changes as you do your differentiation.
Sorry?
Does K change as you do?
No. K is an external parameter.
Set parameter.
Yeah, is a renormalization group parameter. Okay, so you will vary it from lambda to 0. It has no. Well, that's important. You say. There is an associated equation to that which is called the Kalan-Zimanzik equation that corresponds to take not a function this way but flat. Okay? Then you are putting a mass as a regulator. You can't do that. Okay? But the point is, in that case, you don't have real hard separation of scale but very smooth separation of scale. So, in that case, the mass itself, the renormalization group parameter, gets renormalized. So, that's why the equation becomes more involved. Okay? So, in this case, you have a non-local regulator, but which has no ultraviolet effects. Okay? That's the improvement of Vorticity. Okay. So, what to do with this equation? Because now we have an exact equation. The problem is nobody knows how to solve it, of course. And we could say, well, there is a big quantity of exact equations. There are many exact equations. For example, there is a Schwinger-Dyson equation. They are exact in principle. They describe completely the system. So, what is the interest of an exact equation? I would say nothing. The only interest for this equation to be exact is that you know if you perform some approximation on this, the errors that you introduce are in your approximation and not in the equation. Okay? So if you can improve your approximation, in principle you are able to approach the exact theory as long as your approximation gets improved. If you have a non-exact equation, even if you had a very, very good sophisticated approximation, your result will not be approaching the exact theory because your starting point is not exact. But this is the only point, okay? The good point of this equation is not, the main point is not that it is exact. The main point is it has these good properties I mentioned you before. It is dominated by a single scale momenta, and in order to know what happened at a given scale, you only need to know what happened in a neighbor scale. That's the good point. So approximate. So we will look for approximations in order to solve this equation because we are not able to solve it exactly, at least in non-trivial systems. Okay? So, how to do? Well, the first thing you can do, you are able to do in this context, is to use perturbation theory. you know how to use perturbation theory, and if you use perturbation theory in this equation, you recover the standard perturbation theory. And if you use RG improved perturbation theory, you recover perturbative RG. There is no mysterious on that. This equation gives you at the perturbative level, give you the same that perturbation theory. Of course, I would not advise you to use that in order to use perturbation theory. Okay, there are much simpler ways to do that. Okay, so don't use that for perturbation theory. You are able to, but it's not very useful for that. The interest is to use other kinds of approximation. So I will present one kind of approximation, which is the most used in this context. Yes?
You're looking at the flow of the effective action. One can also look at the flow of the bare action, right?
Yeah.
And then take the effective action at the end of the case.
Yeah, you can do that. In that case, you arrive to what is called the Vorticity equation. But one can prove that this is much better, because this formalism, the Vorticity formalism, what one should see is that this functional gamma behaves much better than W. The Gibbs free energy behaves much better than the Helmholtz free energy. And the Vorticity equation is very intimately related to the flow of W. But the flow of W doesn't behave as good as this one. So people have looked at the Vorticity equation, but it has not very good properties, not better than perturbation theory. So I will not advise. There are people that are still trying to use this formalism. This is the old Wilsonian formalism, but people more or less abandon that because even to look for two loops corrections it's become extremely involved. Okay, here two loops is trivial. Two loops in the Wilsonian or Vorticity equation is an aim. It can be done, but it's very hard. Okay, so I would not advise you to use the Vorticity formula. So before doing approximation, let's look to a particular case of this equation. Let's evaluate it in a constant background field. Okay, in a constant background field, this equation, the Gibbs free energy is proportional to the volume and to the running effective potential. Is like in a constant, if phi x is equal to phi gamma k, then you will have again the volume times an effective potential. And the equation now can be written easily because if you are in a constant background field, we know that the system is spatial invariant, so you can deduce that it is simply 1 over gamma 2 of q plus r prime. Where here is just, this is the 2-point vertex in presence of this background field. Okay? And here you see the problem. We have now an equation for the effective potential that is exact. This is an exact equation. Okay, there is no approximation here. This is just to evaluate this in a constant background field. Okay, but now this is not a closed equation because in order to know how the potential evolves, you need to know the 2-point function, the second derivative. Okay, so if you are very smart, you can say, well, let's look at the equation for the 2-point function. Okay? I can write it here. Takes this form. G is just this expression. I will call you G of Q. Okay? So it takes this form, gamma 3 pi Q squared G pi Q minus 1/2 of gamma 4.
Very good.
Okay?
How do you get this?
Oh, and I didn't prove that, but simply take this equation, take two functional derivatives, and you evaluate it in a constant vacuum field. Okay? An easy way to think about it, this has a one loop structure. Okay? So if you know that diagrammatics, this is just, this term is nothing but this diagram, and this one is nothing but the tadpole. But if you don't know anything about diagrammatics, it doesn't help you. But here you have Q, here you have top P plus Q, 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 Q. Okay, and the cross is the intersection.
And it's the full propagators, it's not the bare ones.
Full propagators, yeah, here also, and full vertices. Okay? So again, you see, we didn't want, this is, sorry, gamma 2. Again, we didn't want anything, because now we have the equation for the 2-point function, but we need the 3-point function and the 4-point function. And if you are very smart, you can continue and deduce the equation for the 3-point function and the 4-point function, and you know how the game continues. It never closes. Okay?
You could factorize it.
Okay?
You could factorize it.
Oh, if you know how to do that, I will be glad. I think there is no closed form. And this is a typical problem of the endpoint, the n-body system. The equation for the correlation is not closed. So in order to solve it, you need some approximation. So I will present an approximation scheme that is the most used in this context, and it is called the derivative expansion scheme. Okay? So how does it work? And this is not the only approximation scheme that is used. There are many of them. I present one of them, which is the simplest and the most used, but there are others. Okay? I will not have time to explain anything about this approximation scheme, but if you understand it, it's okay. Well, you see, now we want to use the structure of the equation. The equation, you see, it is bounded. Here, this integral is bounded by k, because this function decreases rapidly. Okay? At the scale k. So we only need to know that for momenta smaller than k. We don't need to know it for any momenta. Only for momenta smaller than k. Okay, so the idea is, well, momenta smaller than k. Let's think first of all what happened at zero momenta. This is the simplest case. And at zero momenta, we have very good news. Gamma 2, when q squared is 0, what is it? Gamma 2 at zero momenta. Gamma 2k. Remember that the delta 2 has been subtracted. It's not computed. Sorry? I didn't know. No, R has been subtracted. So R is already explicit here. You see, the R. Sorry? Little r, yeah, little r. But remember, here we are in an external constant field, so then there is not only the little r. At zero field, there is the little moving r, of course. But if you have the whole function, what is it? This is an exact expression.
Second derivative of gamma?
This is the second derivative of gamma, but if you are at zero momenta, taking the derivative with respect to zero momentum field is like taking the derivative with respect to zero momentum. If you have zero Fourier component that corresponds to a field that is how in the space? Constant. So taking the derivative with respect to field at zero momenta is to take the same thing that taking the derivative with respect to the constant external field. So this is nothing but the second derivative of the potential. And that's just great, because you see there is one part of this function that you can relate to the function that you want to calculate. That's good. Okay? The problem is, of course, you don't need this only at zero momenta, but all momenta between 0 and q. So the strategy is to say, well, at zero momenta I know the function. I know that this integration domain is bounded. So I will perform an expansion in q. So I will do that. I will say that gamma 2 of q of phi at leading order, let's say at zero momentum expansion, I take that. This is zero momentum part. But of course, there are other terms that come here that are polynomial. Well, they are not polynomial, of course. But you can make a polynomial expansion because this is bounded in a finite domain. So at leading order, what you put is here only the bare contribution. But this was already in H. You know, in H you have the gamma 2 of q squared in H is q squared plus r0 plus q0 over 2 phi 2 squared. Okay? So this momentum dependence, you don't want to skip it. You want to keep it because it's already there at one loop. If you don't keep it, that the equation is no longer true at one loop. That's too bad. Okay? So you keep the bare contribution, but the part that depends on the zero momentum part, you leave it to flow freely. Okay? So you arrive to this equation that now it is closed. And it is called the local potential approximation. Okay, but somebody, you may ask, oh, okay, but this is a good approximation, this is a bad approximation. Why to do that? First of all, it has some good features. So it is exact at one loop, okay? Because if I replace here this by the running potential at one loop, it gives you all the one loop contribution. So at one loop you are okay. In 4 minus epsilon, it's okay. There is no problem. But moreover, you can say, I can, this is the in order only approximation, but I can go much far away. I can continue. I can say, here I took a zero order expansion, but I could take higher momentum. Yet I can look at this term in q squared to see how it evolves. Instead of looking only to the potential, I could look at what happened to the term with two derivatives. You see, momentum corresponds to the derivative in the direct space. If you are in the Fourier space, your momenta. If you are in the direct space, there are derivatives with respect to the space, the position. So you can say this approximation, which is called LPA, local potential approximation, okay, is the zero order of an approximation scheme. That corresponds to take gamma k and ansatz gamma k that take this form. In the part that contains derivatives, you only take, that's LPA. Gradient phi to square, but you take a freely evolving potential. Okay? That's what's called LPA. But you can also go a further step and say, well, let's go to the next order of the approximation scheme. This is called order derivative to the square, and then you will have The potential, of course, you continue to have it, but you will consider also how this term evolves. So you take a three function here. Okay? And you have then two functions. Or you can go even to power 4 in derivatives. Okay? So you have these two terms plus all terms with 4 derivatives. You take all terms with 4 derivatives. I give you an example. There are 3 of them, 3 independent. One of them is to the 4. Okay, but you may have also W2 that is, I don't know, Laplacian of pi to square. And there is a third one that you can take as rep and it's fine. Okay? And continue the expansion. As long as you are patient, you are able to go higher and higher. And the point is that this expansion works very well because the domain of expansion is bounded. Okay? You would not be able to do such an approximation in a single Dyson equation because then the integral goes to infinity. So you are expanding in momenta, but momenta goes to infinity. You can't do that. But if momenta are bounded, you are able to expand. Of course, the expansion is an expansion in a parameter of order 1 because you are expanding in Q and Q is bounded by K. Okay? So this approximation only works for momenta smaller than K. Okay? And sorry?
I mean, now you go something which doesn't respect the pi to minus pi symmetry.
Yeah, well, you require this to be this way. I didn't spoke about the parity of this function.
So you have to assume something of the parity of
Yeah. If you want to respect symmetries, you need to impose to this function. With what I wrote, this function to the 5 to the square. But then you put that 5.
Could you in principle violate the symmetry?
Sorry?
Is that, I mean, could you in principle violate the symmetry? Is it something meaningful?
No. If you can show that if your initial condition has a symmetry and the regulator respects the symmetry is respect along the curve. Okay? So this is an approximation thing. I could speak a lot of why this approximation works and why it doesn't work, but I prefer to show you some examples of concrete results. So for example, what are the typical flows of the potential? Well, this is a cartoon of the flow. Let's imagine you are in the broken phase, so you begin, of course, with a potential which tends the system to be ferromagnetic, and when K evolves, the potential deforms, and if you are above the critical temperature, finally you have an effective potential with a single minima and phi equal to 0. How to do that? Well, you must take this equation and solve it numerically. Okay? This is a well-defined equation that you can put in a computer. So you do it completely and you obtain this function.
So you put in an initial effective potential that was in the wrong phase.
It was in the correct phase. The microscopic potential at the microscopic level is always ferromagnetic. You know, if you don't have a ferromagnetic at the lattice space, at the lattice scale, you never can arrive to you don't have phase transition.
I mean, the bare Hamiltonian has a mass, and that mass can be negative or positive.
If you have a positive mass in the bare Hamiltonian, you are always in the symmetric phase, because fluctuations tend to restore the symmetry. If you are already in a symmetric phase, you will be more symmetric. You see? If you begin with a potential which is has already this shape, it will continue to evolve this way. So you will not have a restoration asymmetry. In order to be able to have a phase transition, you must always begin in a potential which, you know, if you don't put in the Ising interactions that tend to align.
I mean, still, even if you start with an Ising model, you could have an exact mapping to a field theory,
Yeah.
a bare field theory,
Yeah.
and then you could look at a very specific temperature,
Yeah.
and then start from this very specific temperature, which has a mass which is positive, and then explicitly calculate.
And you will be in the symmetric space.
Yes.
So you are able to begin with a potential which is already symmetric at the microscopic level, but you will not be able to see the phase transition. In order to have a phase transition, you always need to begin in a broken at the microscopic level, and that makes sense physically. Okay.
What happens if you start from something that's more minimal?
You can do it. To look at first order phase transition, it has been done. You can take a potential which is not polynomial. You can look at a cosinus. All these things that works very well. Okay.
The initial condition you have to take on some kind of microscopic field.
The initial condition, no. For example, people had put look at the equation in a lattice and begin from Ising and calculate the critical temperature to 1%. You can take a realistic microscopic model if you want. Okay? So you don't need to use a Gilbert-Landau. You can use anything you want at the microscopic level. But of course, if you want to keep the lattice, you cannot use this continuum.
What I mean, the information about your theory is in the initial condition.
Of course. The information about your model is in the initial condition. But what happens if you are in the broken phase? In the broken phase, you begin in something which is very similar, but the symmetry, the minimum evolves, but do not reach to zero. And in the intermediate region, the potential tends to a constant. That's the correct physical behavior. This is what's called convexity of the potential. You maybe have listened about the Maxwell construction. Here there is no need of Maxwell construction. The potential evolves automatically to a convex potential, even in the broken phase, but of course you have a non-analyticity here, as you should. Okay? And in the middle you have a constant potential, as given by the...
long-range interactions?
If you have long-range interaction, you cannot use this kind of approximation. This is a very bad idea for long-range interaction. You should do another kind of. So here some result. Here I spoke of the Gilbert-Landau model, but there is a ON generalization. The case I present corresponds to n equals 1, and here there are the results in equal to of the order 2. This is this approximation level at equal to, and you see it's not so bad. Here you have the results from Onzager, and you see even at this low order approximation in a quite complicated situation, a two-dimensional model gives you very good result. The n equal 2 case, which is refuted extremely hard, does work also very well. Let's see in equal 3. Well, in equal 3, there are this order 2 and you see it works again quite well. But I don't know if you realize that turns in a computer in 15 minutes. Okay? In 15 minutes you are able to obtain this precision level. Okay?
I missed what the different columns are.
Sorry?
I missed your explanation of the different columns in the table.
Oh, sorry. Here's the two exponents, mu and eta, the results obtained from the derivative expansion of order 2 compared to the most precise results for this quantity in the literature. Okay? The reference for the most exact are in the notes. Okay, I didn't have place. Yeah?
In n equal to and b equal to, you have a fixed line, not a fixed point if you do the positional way. How do you see that?
If you let me finish with n d equal, this for d equal 3. If you let me finish with d equal 3, I have a more one more transparently, I will go back to the XY model. So in n equal 1, this is the only case where people have went to derivative to the fourth derivative, and you see that the results are quite good. That they're almost, but the limit here in the precision is not in the approximation, but in the quality of the numerical resolution. Okay? De la Motte, which is the author, one of the authors of this result, wrote me last week to tell me that they have new numerical results for derivative to the fourth that are in the error bar of that. Okay? So the main source of error here are not the approximation, are the numerical resolution that was not very good in that paper. So the conversion is impressive because this works in a computer in half an hour.
If it's half an hour, why is the numerics so bad?
Well, because the numerics they made here took 1 month because they made it in a very bad way. So now they decided to change their numerical strategy, and it works in half an hour. It's much more precise, and they can see the convergence of the algorithm, and it works very well. Okay. Okay. So XY. Do you know costless transition? Have you listened about that? Okay. This is a very complicated model. And here we are not able, I never done xy equal to, but people who have done are not able to see the line of fixed point. Okay? What they see is a quasi-fixed point here, a fixed point here. So there is a small evolution here. The beta function is almost 0 here, but not exactly 0. And here they have a fixed point. Okay? So the exponent they write are obtained for this point, which is the one which gives you the 1/4. Okay? And here you don't have a true line of fixed point, but you have instead of the typical flow that way, here you have a small evolution. Very small. Okay? So in the time, let's say, if you don't take fluctuations of the size of the universe into account, you may say you are flat. Okay? They are very, very, very tiny. But they say they manage to see, for example, this scaling. You know, this scaling which is non-analytic. They are able to calculate that. Okay? So they quite well control that.
But I mean, you see the exponents, but how do you see the vortices and the...
That's a good question. Well, the good thing about this approximation, I would say, is that you don't have to care which are the configuration in the space that you are iterating.
I would like to know.
Yeah, well, that's a good point. You may say, well, I would have... I learned in the school costless tablets and vortices and so on. I want to know the relation. Well, what people know is at least one part of the contribution of vortices are there, because if not, there is no costless tablet transition. So these contributions are there, probably not exactly, but they are there. If not, there is no transition. But people do not know how to do the mapping, say. Well, I said what I wanted to say in this first lecture this morning. In what concerns the out of equilibrium stuff, I will tell you about that this afternoon. Yeah?
But I don't understand the question. In the standard RG, you cannot find vortices on the possible third as you put it, right? It's input. You sort of... I mean, in the conventional theory, it's not like it comes out of RG coming your vortex.
No, it's not quite true. If you take the XY model and you make what is called the spin waves approximation, you lose the vortices. But if you begin with the real XY model, the vortices are there. But of course, people don't do that. They don't
come from the XY model, but they come from the the Villan model, which is supposed to be the same universality class, but that contains vortices. So people, in a part, they eliminate vortices and put them again. Okay, this can be justified quite well. But here, no, there is no need of anything. They begin with the Gisborne-Landau model at the microscopic level. They can begin with the XY. Okay, and they are able. All the non-universal property can be calculated as well. I say rising critical temperature for different latitudes can be calculated at 1% level.
Well, we kind of adiabatically entered the question session, so let's just continue with that. But first, more questions.
One comment. Your RG coefficients will actually be partially differentiable.
Yeah, partially. In this kind of approximation scheme, they are partial differential equations. Yeah.
And one more thing. I mean, you just did a derivative expansion.
Yeah.
For example, when you're varying the expansion, why did you assume the potential will be the same polynomial? I mean, there could be newer terms generated, right?
I didn't understand.
The VK,
Yeah.
the potential. That you assume same and are putting in higher order gradient terms. But there could be new polynomial terms that can get generated.
Non-polynomial derivatives.
No, I'm saying polynomial terms. They can come.
Oh, you see, the effective action has all powers of momentum. Okay? When you integrate, okay, a shell of the gamma, the true physical Gibbs energy, contains all powers, all possible terms that are valid, allowed by symmetries. Okay? In particular, this one, but they contain much more terms. You are truncating here at an infinite hierarchy. Okay? So these terms with higher powers are there, that's for sure.
No, I'm not saying about the gradient terms. I'm saying about the polynomial terms. The VKF phi. What is the form of the VKF phi?
There is no restriction to this. It is not polynomial. It has all power of phi. If you expand it, you have all powers of phi. It is not polynomial. Okay? It's an analytical function. You can show that the word is called Gibbs analyticity. No. But there is a theorem that shows that even when k goes to 0, the correct scale function here is analytical. So as long as k is different from 0, this is an analytical function. Only the non-analyticity appears when k goes to 0. So you should be able to expand also in phi. But people have done that. In fact, the bad numerical strategy is to do that. Is to take this function and expand them. Okay? And look for the flow of couplings. And there you don't have any more partial differential equation. You have ordinary differential equation. But this is a very bad numerical strategy.
How do you do that then numerically? How do you represent the function?
You put a lattice. You put a lattice in and you discretize the equation.
On a momentum space, you put a lattice in the Q space.
No, in the Q space, these integrals are done numerically, but almost exactly, I would say. A lattice in phi. The equation is a partial differential equation in k and phi. Okay, so Q here is a trivial stuff. Okay,
so it's a lattice in k and phi, right?
Yeah, and this much better.
There's all this. There's an art in choosing this function R, if I remember, the capital function. It has to have these requirements. There are lots of functions you can have.
Yeah.
I remember about 5 to 10 years ago, people were still fighting out which is the optimal way to.
Yeah, they still don't. Well, in fact, what happened is the following. The physical result cannot depend on R, but because this is simply says in which order you integrate things.
Okay? So at the end, you integrate everything, so at the end, you should have the
Well,
same.
if you do it exactly, which you not doing.
Okay, if you are exact, it doesn't depend on R, but of course you do approximation, and of course the result depends on R. So, what R to choose? Well, I discussed some lines that in the lecture, but the lecture notes. But the point is, first of all, if the dependence on R do not get lower when you are at higher orders, you are making something wrong. Okay? So, first of all, people observe that the dependence on the function gets lower when you go to higher level of truncation. Second thing, people what normally choose is they took families of regulators, okay, and use the principle of minimal sensitivity to a given order. Okay, so they say the true result should not depend, the exact result should not depend on R. So the best result in a given approximation is the one that depends less on the function, and this is empirically a good, normally is the best choice. Okay, and after that you can vary in families of functions and compare. And what people have learned, they have now quite well knowledge on the subject. They know that in order to be able to go to high order, it is important for this function to be C infinite, to be a smooth function, infinitely smooth function. And one of the things that people know, it must not be too sharp, because if you are near and not an elliptical function, nor too flat. Okay? In between, you can find all the lines. The important point is that if you go to the following order, you must verify that your dependence on R gets reduced. Okay? And asymptotically, they should disappear, at least in a finite domain. Another questions
aside from adding?
Yeah?
No, adding.
You said there's a principle of minimal sensitivity. Have people thought about a variation principle in some way?
Yeah, people have thought about that. The German group, Pawlowski, has worked on this, but I do not fully control the results. It's more or less based on this idea, and they look for a sort of ideal choice of R. I'm not quite convinced that this is a very good, because you see, many people do the inverse. They say, well, at a given order, the dependence on the regulator is an estimate of the size of your error. Because if your results vary a lot when you change the regulator, you know what is the quality of your approximation. So you vary the regulator and you have at least an idea of the error bar. Normally we don't publish error bars because they are not very controlled, but we know at least the number of digits. Just doing that, varying the regulator, is a good estimate of the size of the error, and this way we are able to at least guess the order of magnitude of error bars. Yeah?
I'm trying to ignore you. All right, one more.
Is there something known about the convergence of the expansion? Delta 4, delta 6, or whatever?
Well, that's a very. I will use my secret window. Yeah. This is a paper of Peliceto and Vicari. Okay. We don't know the convergence, but I will say something that is related to convergence. So let's look at the 2-point functions. S here is a 2-point function. Okay? Here the susceptibility has been factorized. So this is gamma 2, let's say, at 0 extremity. So you can normalize it. Instead of representing it in terms of the momenta, you can represent it as the product of the momenta and the correlation length, and you can show that this function scales in the critical limit. Okay? So normalize it in this way, factorizing the chi and represented in terms of q, the function begins with 1 plus q. So the question is, does these terms of higher order are smaller or are small or not? Okay. Well, sorry, I went too fast. Here you have the expansion at Morse cube. Here are the coefficients, okay? And you see that the coefficients are quite small. That's an indication that the rate expansion is a good approximation. There is a small parameter. We don't know how to use it, but there is a small parameter somewhere. And you see that, well, there are some debate of the precise value, but the order of magnitude is quite clear. It's very small. The following is also very small. And there is a theorem. I do not fully know what is the level of rigor of this theorem, but I can explain you in detail that for large n, for large orders, the coefficient decrease are alternating sign decrease, so there is a finite radius of convergence. Okay, and quite large. Okay. So
see, this is when you ask questions, you might get more than you ask for. I think at this point we should terminate the discussion officially and have it informally over coffee and reconvene at 10:45. Remember that we have an optional informal final lecture by Nicholas on the non-equilibrium stuff at 1:15. If you want to.